All right, hello. We are on Unit 2, Video 1, and this is horizontal projectile motion. We are going to start talking about projectile motion, what it is, how we solve for things and objects that are moving in both the x and y directions. And then we're going to use the big three equations we talked about last time to solve problems with projectiles. All right, so here we go. First thing we need to do is just remember what we talked about in our last unit about which variables we use when things are accelerating versus which variables we use when things are at a constant speed. So I want you guys to just think about it for a second, write down the variables here for the first for accelerating objects and then the three variables for objects at a constant speed. Okay, so pause the video, write them down if you can on your own, and if you can't, then I will go through them. All right, so things that are accelerating, okay, we have the final velocity, the initial velocity, acceleration, time, and displacement. Okay. For things that are not accelerating, we have three variables. We have displacement, velocity, and time. Okay. So that's really important to remember. So remember, this is when acceleration is not zero. This is when acceleration is zero. Which equations would you use in each situation? Okay, for the ones that are not accelerating, the constant speed. So when a is zero and we have a constant speed, you'll only have one equation. It's v equals d over t. Okay, so you have no choice. That's it. When a is not zero, you have three big equations. So we call them the big three. Okay, and those are the equations you use when acceleration is not zero and things are speeding up or slowing down. Okay, a projectile is any object that's being acted upon only by gravity. Okay, so examples would be a football, a bullet, a pole vaulter, a diver, a soccer ball, anything that's kicked into the air, thrown into the air, dropped in the air, rolled off of a table, anything like that. Okay, projectiles travel along parabolic paths. That means they follow some sort of path like this or like this. So part of a parabolic path is still a projectile. Okay. Since gravity pulls objects straight down toward Earth, acceleration is only in the y direction. Okay, so gravity always acts downward. Okay, so gravity is always in the y direction. We will ignore air resistance for this unit, and since we are doing that, there is no acceleration in the x direction. So we're going to imagine there's no air, so nothing is pushing or pulling anything in the x direction, in the horizontal direction. So their acceleration, basically what this is saying is that a equals 0 in the x direction, or in the x-axis. And up here we're saying a equals negative 9.8, or gravity, in the y direction. Okay, that's very important. It's going to come up a lot here. I'm going to zoom in on this picture here so that we can get a good look at it. All right, so for this picture we have a cannon shooting a cannonball out, and we are going to draw the x and y velocities for the cannonball. Okay. So the cannonball gets shot out to the left, okay, and when it first gets shot out, it is moving all in the x direction. So we're going to say that's the x velocity. Once gravity hits it, then it starts to move downward. So we still have the movement to the left, but we also have a little piece in the y direction going downward. Since there's no acceleration in the x direction, in the horizontal direction, these arrows stayed the same size. Since the acceleration of gravity is pulling the ball down, the Vy gets bigger for every second that passes. So as we continue, Vy gets much bigger. Okay, so that's what it should look like. Now in these problems for projectiles, we're going to break up our data into an x-axis and a y-axis. We cannot mix these two things, okay? So to describe the motion, we have to make these two variable charts. Since there's no acceleration in the x-axis, we only have 3 variables, as we mentioned up here. So remember, a minute ago, we went through when things are accelerating versus when things are not accelerating. So since we have no acceleration in the x, these are the only 3 variables we're going to have. Since we do have acceleration in the y, that means that we're going to have all 5 variables in the y. Okay. This also means that for x-axis, we only are going to use this equation. And for y-axis, we're only going to use the big 3. Okay. A couple of notes down here. The y direction motion must include gravity, and therefore the downward acceleration, or the downward velocity will increase with time, meaning it's going to speed up going downward. The x direction is always at a constant speed. Okay? And time, this is really important. Time is the only variable that is the same in both directions. This is really, really, really important. So put a big star next to it. Okay? But basically what that means is that we can take the time in the x direction and we can move it over here to the y direction. They will be the same no matter what. Okay? And that's because it can't land on the ground in the y direction, but not land on the ground in the x direction. So that's sort of the idea. All right, let's move to some examples. So go ahead and flip your page. Okay, here we go. So today we're solving for horizontal projectiles. Horizontal projectiles. What that means is that when we start, we are only going to have motion in the x direction. And the key thing about that is that if it's a horizontal projectile, and we only have motion in the x direction to begin with, then that means that the initial velocity in the y direction is going to be 0. Okay, only for horizontal projectiles, but that's what we're going to be working on today. There are 3 basic problems that you can solve for, so how fast, how high, how far, okay, in these ones. And what we're going to do is, you don't have to draw this chart every time you set up, but these are sort of the steps that you would take in order to solve these problems. So we're going to kind of go through those steps for each of these problems. You would definitely want to draw a picture. If you don't draw a picture, you're definitely going to miss points. Example 1, a ball is rolled off the table with a velocity of 5 meters per second. So let's draw it. Doesn't have to be pretty, but it does need to be accurate. And then what you'll do is you'll kind of project what you think the ball will do, and based on your life experience, you should know what would happen if a ball rolls off a table. If the table is 1.5 meters tall, so let's make a note of that, okay? How far from the base of the table does the ball land? So we want to know how far from the bottom, the base, does that ball land? That's what we're looking for. So you sort of have to go through and figure out what you're given, okay, just like in the previous unit. So remember, in the x-axis, we only have 3 variables. So let's think about it if we know these things. The velocity in the x direction is never going to change, so once you have it, it stays the same. Nice thing is, since the ball rolled off horizontally off the table, we know that all this 5 meters per second is in the x direction. The distance in the x direction, displacement, would be how far it moved left or right. So that's the piece we're actually looking for. And we were not given any time, so we don't know that. So let's go to the y. We have initial, final, a, t, d. And let's write down the ones we know. Since this is a horizontal projectile, and this ball is not moving in the up or down direction as it comes off the table, that means that the initial is 0. We cannot say that the final is 0, and the reason for that is that we don't consider when the ball hits the ground, we consider the second before it hits the ground. So you're just going to leave that one blank because we don't know that. The acceleration in the y direction is gravity. That's what's pulling the ball down. Okay. We don't know time. And the displacement in the y direction is how far it fell or moved in the up or down direction. So since it went from the top of the table to the ground, and the table is 1.5 meters high, we know displacement is 1.5. Now remember, displacement is a vector, so we need direction. And since the ball falls down, it should be negative 1.5 meters. If you miss that sign, the problem's going to come out wrong. So be careful. All right, now this is a little note here. Start with the axis with the most information. So we are looking for this, but as you can see, we can't find it. Okay, the equation won't give it to us because we have two unknowns. So what we can do, and this is the part about time being important, is we can find the time over here, put the time over here, and then we can solve for D, which is our ultimate goal. So if we're trying to find time here, then we don't care about VF. The only equation that we can use is that one. Okay, and I'm just going to go ahead and plug in. So negative 1.5 equals 0 times t, which 0 times anything is 0. Oops, not cubed. Weird. Okay, and if you solve for t here, you get 0.55 seconds. Okay, so 0.55 seconds, move it over here. And now you have enough in this column to go ahead and solve for the ultimate goal, which was displacement in the x direction. So since the x direction, we only have 3 variables, we're going to use this one. Okay, 5 equals d over 0.55, and you get displacement equals 2.77 meters in the x direction. Make sure you have units and you box your answer. Okay, let's do another example. All right, a bird flying at 15 meters per second. So he's flying this way. Poops above an unsuspecting crowd if the poop lands on a 2.0 meter tall student. Okay, so that guy's 2.0 meters tall. After falling for 2.5 seconds, so we know the time is 2.5 seconds. How high above the ground is the bird flying? So we want this distance. Okay. Now, I want you to make a note that since it's going to land on the kid's head, the 2.5 seconds of falling is only going to take us to this height. So once we find the displacement that it falls in 2.5 seconds, we're still going to have to add these 2 meters to get the total distance to the ground. Okay. But let's start with x and y, and we'll kind of walk back through that in a minute. Okay, 3 variables here, 5 variables here. Some givens that you already know for sure are that gravity is acting on the bird poop. It's a horizontal projectile, so the initial velocity in the y direction should be 0. They've given us the initial velocity in the x direction. Okay. And they've given us the time. Now, yes, we could find the displacement in the x direction. That would tell us how far the bird poop traveled, or the bird traveled, whatever, in 2.5 seconds. But no one asked about that, so I don't know why we would do extra work. So what we do want to find is the displacement in the y direction before the poop landed on the kid's head. Okay, and since we don't have VF and we're not trying to find it, we're going to use that same equation that we used last time. Okay, so if we plug in, 0 times anything is 0. And if you solve that, you get displacement equals 30.6 meters. Now, remember, this is just to the top of the kid's head. So if we want the bird to the ground, we need to do 30.6 meters plus 2 meters. So the total would be 32.6 meters. Okay. All right, last example, and it will be the simplest example. So hopefully it's just getting a little bit easier here. Okay. A car drives off a cliff and lands 3 seconds later. Okay, that's our time. It lands 50 meters from the base, so we know that this distance is 50 meters. And we want to know how fast was the car going when it left, okay? And it's driving off a cliff, so it's driving straight. And then it's going to sort of fall like this. X and Y. 3 variables here. 5 variables here. Let's write down our known variables. We know this is negative 9.8 because gravity takes effect over the car. We know this is 0 because it's a horizontal projectile. We know the distance from the edge of the cliff to the car, so in the x direction, since that's horizontal. We know that the displacement is 50. We know the time is 3. And we want to know what speed the car drove off with. Now, we already know the initial velocity in the y is 0. So we want to know the initial velocity in the x direction as it left. So we're looking for that one. Should be pretty easy. We don't even have to use this column. Okay, we have one equation for the x direction. And so if you do the math here, you plug it in, you get 16.7 meters per second. Okay. We are going to do a demo in class, and we're going to work with this all next class. So make sure you understand the overall concepts, and we will start practicing this and getting good at it when I see you next.